talk about Alexakis theorem on conformal invariant integral. Thank you.
All right, let me start by testing the microphone. Great. Okay. It's a pleasure to be here. I want to join the other speakers in thanking the organizers. This is a wonderful conference. I feel particularly ridiculous at having to disappear right after my own talk. Anyway, all right. I would like to try to explain at least a part of Spiros Alexakis' remarkable proof of the Deser-Schwimmer conjecture. So let me assume that you know essentially nothing about the problem. I'm going to try to explain it from the beginning, and then explain how you prove I think the most striking single idea in the proof. Although at the end of my lecture, still you will not really understand. I think it's fair to say you'll not really understand how the proof goes. All right. So we're going to talk about conformal integral invariants. Okay, what is a conformal integral invariant? Well, we're going to live on an even dimensional manifold. All right, we're going to fix a dimension n. And for that fixed dimension n, we're going to look at a metric. And in a coordinate patch, of course, the metric is given by a gij. And we're going to form a polynomial p in... Oh, all right. Let's see what... Now, let's... Wow, all right.
It's like the light, because your hand also had this...
Thank you. Look at that. Thank you very much. The lecture is much clearer. Okay, thank you. Yes, okay. So we're going to make a polynomial in the derivatives of the metric and in 1 over the determinant of the metric. Okay, we regard these, let's say, as formal variables, and we make a polynomial p. And then we're going to say that p of the metric is that polynomial. So given a particular polynomial in these formal variables, then once you are supplied with a particular metric, you can look in a coordinate patch and evaluate p of g. Now, this will make no sense unless the quantity p of g is preserved by isometries in the sense of the transparency, which, thanks to much needed technical help, we can all now see. Okay, so the polynomial should be preserved by isometries, and a conformal invariant, before anything else, had better make sense in as on this transparency. Okay, so that's the first main property. Now, all right. So that means that in some sense it makes sense. It is well defined pointwise. Okay, but now we want its integral to be to have a conformal meaning. So we fix a manifold and we take a metric g and we make a conformal deformation of the metric by multiplying it by this factor e to the 2 phi. Phi is any real valued c infinity function. All right, that's the new metric g hat. And what we want is that the integral over the manifold of the polynomial associated to g hat, integrated with respect to the volume element for g hat, should be the same as the integral over m of p of g for the volume element of g. So this means that pointwise the polynomial has an invariance under isometries, whereas the integral of the invariant over the manifold has a further invariance under conformal deformations. Here, M is supposed to be a smooth, compact manifold without boundary. Okay, when I say a manifold, that's what I mean. Okay, and one final small point, which is that I want the integrand P of G to be dimensionally correct. The integral over a manifold, over an n-dimensional manifold of the quantity P of G should be a dimensionless quantity. Distances have the dimension of meters. Derivatives of the metric tensor therefore have the dimension of meters to the something or other power. and the integral of P of G should be a dimensionless quantity, and that's reflected by a simple invariance property that I've given here under constant scalings, okay? And so I want to assume that. So a polynomial with those properties is simply what I call, what everybody calls a conformal integral invariant, or maybe the integral of that should be called a conformal integral invariant. Anyway, that's the definition of a conformal integral invariant, okay? Now, the problem that is solved by Spiro's proof of the Deser-Schwimmer conjecture is simply to find all possible conformal integral invariants. This is a problem with serious applications, but today I'm not going to speak of any of those applications. I'm just going to I'm going to discuss a few points in the proof of the solution of the problem without worrying about why one cares. Okay? So, all right. Now, all right, so find all possible conformal integral invariants. The short description of the answer is that there are three obvious ways to produce conformal integral invariants, and the theorem will say that every conformal integral invariant is simply a linear combination of the three obvious things. All right, so let me explain what the three obvious things are. By the way, so this lecture is supposed to be clear and easy, which can't be said for the whole proof. So please interrupt if anything isn't clear and easy. Okay, so three obvious examples of conformal integral invariants. Okay, well, first of all, we can have pointwise conformal invariants. So suppose that it happens that whenever you make a conformal deformation of the metric g, so here t is not a constant but a c infinity positive function. Suppose that whenever that happens, the polynomial p has a pointwise transformation law. Okay? Well, of course, if there is a pointwise transformation law, we can simply integrate the pointwise transformation law and conclude that the integral of p of g is preserved by conformal transformations. This factor is exactly made to cancel the factor t to the plus n that would appear in passing from the volume element of g to the volume element of g hat. Okay? So that's one way. Okay. Now, of course, all right, so I call that an example, but of course I haven't written down any particular polynomials that do that. So let me just write down an example of the example. All right, it depends on the dimension, but for example, in dimension 4, we've seen in, for instance, in Sophie's talk yesterday, the norm squared of the Weyl curvature, and in dimension 4 that has the correct scaling, the correct dimension, so that its integral is a scalar. And this is a pointwise conformal invariant, as everybody knows who has thought a little bit about conformal geometry. Okay, so that's the first way to make conformal integral invariants. The second way to make conformal integral invariants is to take exact divergences. So what I mean by that is the following. Suppose that on our manifold we produce a tensor. So the tensor has components, ti. And let's suppose that each ti, each component of our tensor, is a polynomial in the same variables as before, formal variables, the derivatives of the metric tensor and 1 over the determinant of the metric tensor. Okay? And let's assume that this t is intrinsic in the sense that it is preserved under isometries, but of course it transforms as a tensor rather than simply as a scalar. All right? So suppose that t is such a thing. Well, if t is such a thing, then obviously its divergence is a conformal integral invariant for a trivial reason. When you integrate an exact divergence, guess what? You get 0 by integration by parts or Stokes' theorem or whatever you want to call it. So you always get 0, and 0 is spectacularly invariant under conformal changes of the metric. Okay? So that's an obvious way to make a conformal integral invariant. Here, notice it's important that our manifold is without boundary. Okay. Let's, again, that's an abstract discussion. Let's give an example of the example. And so I picked one in dimension 6, more or less out of the hat. Let's say our tensor T is the gradient of the norm squared of the full curvature tensor. Of course, the full curvature tensor has no particular invariance under conformal rescalings of the metric, but nevertheless, it's the divergence of this tensor, which is then the Laplacian of the norm squared of the curvature, obviously integrates to 0 because it's the Laplacian of something. All right, so this is an example of the example of a conformal integral invariant. So far, we have two ways to produce conformal integral invariants. We have pointwise conformal invariants, and we have exact divergences. Okay, and now there is a third example, very simple, the Gauss-Bonnet integrand. So the Gauss-Bonnet theorem gives us a specific polynomial, the Pfaffian, whose integral over the manifold is the Euler characteristic. The Euler characteristic of the manifold is, of course, again, spectacularly unchanged by conformal deformations of the metric, and therefore the Gauss-Bonnet integrand is obviously a conformal integral invariant. So now we have three ways to produce conformal integral invariants. All right. Now, Deser and Schwimmer, two particle physicists, asserted in 1993 that every conformal integral invariant may be written as a sum of a pointwise conformal invariant, an exact divergence, and some coefficient times the Gauss-Bonnet integrand. Okay? Depending on which physicist you talk to, you may or may not hear the assertion that this is obvious. Okay? Okay. However, no matter which physicist you talk to, I think if your goal is to come up with a proof, you will not hear anything useful. Okay. So let me call it then all right, so the Deser-Schwimmer assertion. And the Deser-Schwimmer assertion was proven by Spiros. And let's see, this was a long, long process in which he produced many iterations, and I went through them trying to understand and checking very carefully. And so exactly when this thing was solved is an accounting problem, but let's say it was solved in 2006. Okay. Okay, so I would like to explain at least one of the main ideas in Spiros' proof. So for that, I would like to give some background. Okay, so all right. So So the first bit of background is Hermann Weyl's invariant theory from the 1920s, and so this says the following. So suppose we have one of our polynomials in the derivatives of the metric and in 1 over the determinant, and suppose that this thing is preserved under isometries, but let's assume nothing else, no conformal invariance, nothing about the properties under constant rescalings, just this. What can this thing look like? And according to Hermann Weyl, this P is simply a linear combination of something whose invariance under isometries is very obvious, namely contractions of tensor products of covariant derivatives of the metric tensor. I'm sorry, of the curvature. So we take the full curvature tensor, and we possibly take let's say its 11th covariant derivative. And then we take another factor in which, let's say, we don't differentiate it at all. And we take some finite number of factors, and in each case we decide how many times we're going to differentiate the curvature tensor. We then take the tensor product of all of those, okay? And now we have a great big tensor with a whole lot of indices. With any luck, there are an even number of indices. And so then you introduce some pairing of the indices, And once you have paired up the indices, you can then contract in all indices with respect to the metric. And that's what this expression means. That's what a C nu means. And so it's determined by how many times you differentiate each factor, how many factors there are, and how you decide to pair up the indices. So that's let's say, a complete contraction, and a linear every Weil invariant is a linear combination of complete contractions. So that's Hermann Weil's invariant theory. Very easy given the least little bit of representation theory, and going back to the 1920s. Oh, yes, yes, sir.
Is there a reason to choose those variables? Why not, for example, determinant itself?
The determinant itself is a polynomial in the derivatives, so it's included. So that's included. Let's see, why is that included? So, for instance, you would like to take the inverse of the Gij, and in fact, what one could, instead of taking that determinant, one could take simply the inverse of the Gij. It would be the same theorem. Okay. Okay. So that's Hermann Weil's invariant theory. So now we know what P of G has to look like, at least given the first of these invariance properties, but not given any conformal information. So that's the first thing that comes from elementary invariant theory. There's a second very, very important fact that comes from elementary invariant theory. This comes from the second theorem, or the second fundamental theorem, whatever it's called, of classical invariant theory. Okay, which is, and well, maybe if there's any interest, I will remind you what the second fundamental theorem of invariant theory says. But let me tell you instead. Let me tell you what information it produces that's relevant to this problem. Namely, for the polynomials P of G that we care about, okay, suppose it happens that you have one of those linear combinations of complete contractions as in the previous transparency, okay, but suppose that it equals 0 all the time. So we've found some very complicated way to produce the polynomials, to produce the invariant 0. If that's true, so then now that's pointwise, that's not an integral. If that's always true, then the fact that this is always 0 can be deduced from certain simple formal rules. For example, the symmetries and antisymmetries of the curvature tensor. Take whatever properties of the covariant derivatives of the curvature tensor you can get out of an undergraduate differential geometry book, write them down, and then declare that you're simply going to apply them. And the theorem is that if our linear combination of Weil invariants is always equal to 0, then the fact that it's always equal to 0 can be deduced from formal rules. Okay? And that follows from elementary invariant theory, thanks to the fact that P of G is not of too high degree because it has the correct dimension. Okay. Another basic bit of background that I want to mention is the ambient metric from conformal geometry, which Robin Graham and I developed in the 80s. If there's time, we'll get into how that enters Spiro's proof. But it is around for people who know more conformal geometry than I do. Let me just mention that the ambient metric is very different in odd dimensions versus even dimensions. In even dimensions, it isn't completely determined. It's determined up to a certain ambiguity. And it happens because our invariants for this problem are dimensionally correct, that, thank God, the ambiguity in the ambient metric plays no role. And so we can act as if it's completely well-defined. Otherwise, life would be much harder. Okay. Now, all right. The piece, all right, that's the end of the background. Now I would like to show you a piece of Spiro's proof. Okay, so what I would like to sketch is something called the superdivergence formula. Now what does that mean? Well, we are given the invariance of an integral. That's what a conformal integral invariant means. We know that a certain integral is invariant. it is surely much easier, and we have our hands on the situation much better if we know that some equation holds pointwise. Okay, and so what the superdivergence formula is going to tell us is that if a certain integral is invariant, then a certain equation holds pointwise. Okay, now we'll see in a minute that it's all but trivial to show that an equation holds pointwise, but that equation is useless. The big deal about the superdivergence formula is that if an integral is invariant under conformal deformations, then an equation holds pointwise, and that equation is useful. Okay. Now, so what does it mean for an equation to be useful? All right. Let me wait 1 or 2 slides, and then I hope to explain, at least not in general, but in the context of this proof, what it means for an equation to be useful. Okay. So let's start. All right. Let's start. So we have P, a conformal integral invariant. Let's make a conformal deformation using a function phi in C infinity. But instead of making the conformal deformation with a factor e to the phi or e to the 2 phi, let's introduce a real parameter t, and let's look at the metric e to the 2t phi g. So t is a real number, phi is a function, and this is the conformal deformation we're going to look at. And of course, we're going to be integrating this invariant with respect to the volume element for the conformally deformed metric. So this depends on t. Now, because this integral is supposed to be preserved by conformal deformations, it is independent of t. And therefore, if we differentiate at least once in t, so L is greater than or equal to 1, we're going to get an integral which is always 0. Now, I would say so far we should not be real proud of ourselves. This is the most obvious thing to do. I hope to convince you by the end that there's something so that Spiros should be real proud of himself. But this isn't yet it, okay? Okay, so, all right. All right, what progress have we made? Well, we started with an integral being invariant, and we have gotten to another integral being 0. Here, we've introduced another ingredient. This integrand depends on the function phi. And notice that the structure of this phi has a lot to do with the structure of p. For instance, suppose that we decided to write p in terms of derivatives of not the metric tensor, but rather separately the Weil curvature and the Weil-Schouten tensor. Okay, and so of course that's an equivalent way of writing things. Well, one thing that will happen if you differentiate enough times like this, so for suitable L, you will find a term in which every Weil-Schouten tensor is replaced by the Hessian of phi. That's simply part of the transformation law for the Weil-Schouten tensor under conformal deformations. Okay, and so whatever structure P had, you will find it very closely mirrored in the I. That's very good. What you would like to do is use the fact that the integral of I is 0 to conclude that you can subtract from I, for example, that you can subtract an exact divergence and make I smaller. Let's say remove some terms from I. If you could do that, then because I very closely reflects the structure of P, you could guess which exact divergence you should try to subtract from P in such a way that that when you do that, and then you look at how the I has changed, it got simpler. Some terms have been removed. Maybe some other terms have also been added, but they're somehow less important according to some very complicated definition of what's more important and what's less important. And so if you could do that, you could successively, by many applications of this, you could successively simplify the I until finally, let's say it's 0. This isn't actually what happens, but just to give the flavor. And so if you could do that, you would be subtracting off many, many exact divergences from P until finally this thing is exactly 0, which means that what you're left with is a local conformal invariant. Now that can't work the way I said it if for no other reason than that it omits the Gauss-Bonnet integrand. But it gives you some feeling that if you know that this I can be simplified by subtracting an exact divergence, that's good news. Okay? And that's because of the fact that the structure of I closely reflects the structure of P, and if this is going to work, the exact divergence that we're going to have to subtract off should very closely reflect the structure of I. Okay? So we will be able to make progress if we can simplify I by subtracting off the exact divergence of something which closely reflects the structure of I. Okay? That's the big point. Okay. All right. That. Okay. Now, all right. Well, let me start with a quite simple observation, which, however, is useless. So I'm going to call this the useless divergence formula. Okay. The useless divergence formula says that if you have a polynomial I of g phi, which always integrates to 0, then in fact it is an exact divergence. Right away, it is, never mind simplified, it contains some terms, it is an exact divergence, and that's easy to see. The trouble is that the thing of which it is an exact divergence does not closely reflect the structure of I, and therefore once you have made this little observation, you're left with the devastating question, so what? Okay? So let me try to explain, nevertheless, the proof of the useless divergence theorem, because it will turn out not to be as useless as it looks. Okay, so the proof of the useless divergence formula. Well, we take, we look at our integration by parts, and let's say our integrand I of phi, etc., it contains at least one factor, every term contains at least one factor that has a phi in it. It isn't just an invariant that involves g. And that certainly happened for us, right? When we differentiated with respect to the t, the way we got these i's, certainly there's always at least one phi floating around. And now, well, this phi is being differentiated in each term. But in each term, you can simply use integration by parts to move the derivatives from that phi to all the other stuff. So you can pick one particular factor phi and just systematically peel off the derivatives. Now, in terms of an integral, integration by parts says that this integral is equal to that integral. What's going on pointwise? Well, remember why integration by parts works. Integration by parts works because the difference between the left-hand side and the right-hand side is the integral of an exact divergence. So if we're thinking pointwise, what we're doing is we're taking this term that we started with and we're changing it by an exact divergence. In the end, what we're left with after subtracting off all these exact divergences is we've got an integral in which all the derivatives have been removed from phi. So we have the integral of phi times some stuff. Maybe this has been polarized. If there were 11 factors of phi, we polarized the original thing so that there are now 11 independent functions, phi 1 through phi 11. And let's say it's phi 1 to which we've done this process. So, so now we know that the integral of phi 1 times some gunk that involves only g and phi 2 through phi 11, this integrates to 0. Okay? Well, in particular, this gunk has the property that you can multiply it by anything and integrate and get 0. So therefore, the gunk is identically 0, and therefore we have a pointwise identity, namely the useless divergence formula. The integrand I of phi g is an exact divergence. but an exact divergence of something whose structure we cannot keep track of. Damn. So near and yet so far. Okay. So, all right, now I believe begins the part that is anything but obvious and all right. So, how are we going to use the useless divergence formula? Well, we know that our quantity I that came from conformal deformations but involves phi, this quantity always integrates to 0. Therefore, it's the exact divergence of something, but we don't really know what. Damn. Never mind, it is an exact divergence. So this equation is true. The fact that it's true always means that it can be demonstrated by applying formal rules like the symmetries and antisymmetries of the curvature tensor. Okay? That's the observation from invariant theory. Okay? So not only is this true, but it follows from applying the formal rules. So what? Watch. Okay. Well, these same formal rules, let's say the symmetries and antisymmetries of the curvature tensor, Ricci identities, whatever, the elementary identities that you find in a first semester geometry book, these hold in all dimensions. And therefore, this same fact is true not only in the dimension little n in which we were originally working, but in all dimensions capital N. Let me imagine that capital N is strictly bigger than little n. The case capital N smaller than little n is not interesting for this. We'll see why. All right, so what we've learned is we have the useless divergence formula, but the useless divergence formula, completely unchanged, is true in all dimensions, not just in the dimension in which we were originally interested in it. Okay? Well, now, all right, that means that the integral of this thing is 0. The integral of this I is 0, but not just in the original dimension, but in dimension capital N. Okay? Now we've gained something crucial, namely this integrand is now no longer dimensionally correct. If distances have the dimensions of meters, the volume in dimension little n has dimension meters to the little n, and therefore this integrand originally had the dimension meters to the minus little n, but now we're integrating over a manifold of dimension capital N, and therefore this is meters to the minus little n times meters to the capital N. This is a dimensional quantity. It is affected by constant rescalings. Okay? Well, constant rescalings are not really what we care about, but let's do the following. So now let's restrict attention to the case in which our phi is supported in one single coordinate patch. Outside the coordinate patch, our integrand is 0 because phi is 0. So we're really integrating not over a capital N dimensional manifold, but only over one coordinate patch. We might as well, therefore, be integrating over R capital N. All right? So we're looking at R capital N, but everything is happening, nevertheless, inside one, let's say, inside the unit ball of R capital N, the single coordinate patch. Okay? Now let's make a conformal change of the metric again, but let's, here I think I've got the sign wrong. Imagine there's a minus sign there. E to the, well, plus or minus xi dot x times g. Here xi is a constant vector in Rn. Now this is a bold move, if for no other reason than that it is, it breaks the coordinate invariance, right? We're in a coordinate patch, and what this thing means depends on our choice of coordinates. And so you can very easily think to yourself, this is obviously complete bullshit. It can't lead to anything. But be patient. Well, in fact, I think it's pretty clear that one could change this whole discussion so that it becomes invariant under coordinate changes, but that would make it no simpler. That would remove complexity from, it would be less weird at some point, but more complicated at some other point. So let's forge ahead and agree that, all right, this breaks the coordinate coordinate invariance, so what? So we've made this change. All right. Now, because of the fact that we are in a dimension other than little n, when we make that change, we're going to get a factor something like this. Okay? So what, if you write down the equation that the integrand I applied to g hat and phi is equal to 0, where g hat is equal to the particular conformally deformed metric from the previous slide, okay, this is what you will get. These are the terms in which you never differentiate the factor e to the I xi dot x. Okay? And here are the terms in which perhaps you do differentiate the e to the I xi dot x, and then you will bring out various powers of xi. So this is a subscript gamma, and that's xi to the gamma. I'm sorry, I didn't write it clearly. Okay?
So this metric G is still in original manner?
Oh, so, well, no, so this metric G is now an R capital N. Okay? So G is an arbitrary metric on R capital N. Phi is an arbitrary function on R capital N, except that it's supposed to be supported in some fixed small neighborhood of the origin. Xi is an arbitrary constant vector in Rn. And that's what this means. Okay, is it clear? All right.
You're working in a coordinate patch now.
Yes, yes. And that coordinate patch is supposed to be, let's say, a little ball in R capital N.
So shouldn't you take into account the integral of the quantity outside the patch?
Ah, but outside the patch, little phi is 0.
Oh, okay.
So we're okay. That's a very, very good question, but I prepared in advance okay, so little phi is just supported in the coordinate patch. Okay? So now this is always 0, and if we had not, notice that if we had not taken the precaution to move to a dimension capital N, we would not see this factor at all. Okay, but now capital N is different from little n, and so it appears. How are we going to use it? Well, the first thing we're going to do, notice we've still got integrals. We're trying to get a pointwise invariant, but this is still an integral. Okay? Now, what I'm going to do next is use some integration by parts to get rid of the powers of xi that appear. Okay? So to get rid of these, I'm going to use this simple fact that if you look at an exponential times xi, you will get up to a sign plus or minus 1 over this coefficient capital N minus little n times the derivative of same. Okay? Now, we want the exponential, we don't want the derivative. Therefore, we integrate by parts to move the derivative away from the exponential and onto whatever other stuff is there. Okay? When we do that, notice that there arises a factor 1 over capital N minus little n. It would be a little strange to try that when if we didn't change from little n to capital N. Okay? Remember also, when you integrate by parts, what you're doing is subtracting an exact divergence. So we have some understanding of what's going on pointwise, not just in terms of the integral. Okay. Well, if you repeatedly do that, you discover that you have the integral of the exponential times the original guy plus these other fellows, which, however, have powers of capital N minus little n in the denominator. There's a tricky point, which is that actually you can put capital N's in the numerator because you can wind up with the metric tensor contracted with itself, which gives you a factor of capital N, the dimension. But nevertheless, the most significant terms are, I mean, if you expand in powers of capital N minus little n, you can make it look like that. Okay? So notice this has gotten rid of the powers of xi, and we have this exponential, and we have capital N minus little n to various powers in the denominator. Okay, now Now, let's exploit the fact that xi is arbitrary. We have here some function of x. Who knows what it is? At least it has compact support because phi has compact support. Okay? And this integral is always 0. As long as capital N is different from little n, that means that the Laplace transform of the fellow in curly brackets is 0. Anything whose Laplace transform is identically 0 is the 0 function. And so now we know that this thing is 0. So we have our original I of g phi plus a whole lot of stuff like this, and that is 0 pointwise, except I should have said I've removed also some exact divergences, so that term should be that, well, this is identically 0, but that also means that if you could, well, okay. Yes. Oh, no. Forget that last remark. Simply, this thing is identically 0. Okay? All right. Now, that's all fine, but well, let's see. What does it tell us? Well, first of all, it's not so easy to keep track of what these guys are. Okay? It wasn't easy before. It's still not easy. Okay? Furthermore, at least originally, we were in the situation where we knew where we live. Our metric g lives in a fixed dimension little n, and now our metric g lives in a coordinate patch on R capital N, and capital N is arbitrarily large. All right, so this looks rather strange. All right, let's see what we can do about it. Well, what we're going to do about it is, first of all, in order to come back home, we're going to specialize now to manifolds of dimension capital N that are the products of a manifold of dimension little n with a flat torus. Okay? If we do that, then of course the curvature in dimension capital N is related in a very simple way to the curvature in dimension little n, and therefore this same equation holds, but now in the fixed dimension little n in the original dimension in which we lived. Okay? So what is capital N doing there? It is simply a parameter. Okay? Aha. So now the thing to do, so this equation holds pointwise in dimension little n, and capital N is just a parameter. Now that that's true, oh.
So phi can't be independent of the torus variable?
Phi will be, wait a minute. No. Phi can be independent of the torus variable because, I mean, if it was compactly supported, first of all, we've gotten rid of compact support, and this is all a pointwise thing. But if that were not true, nevertheless, you know, this isn't, I didn't put here R n minus n, I put T n minus n, and that's compact, so it would be okay anyway. Okay? Okay. All right. All right, so we've got something which is hard to keep track of, but which at least lives in the original dimension, and we have left over this capital N, the relic of the previous higher dimension, and it's a free parameter. We're simply going to let it tend to 0. Anything, therefore, that had a power of a non-zero power of capital N minus little n in the denominator is gone. Okay? And therefore, we know that in the original variables, this is true. All right. Now, it turns out that although if you look at the full, I mean, think about the last n slides, it's very hard to keep track of that whole procedure. There's no way. It's too complicated. But if you know that this is what you're after, you can look at every stage and you can ask, which terms might possibly lead to something in here that survive when capital N goes to 0? So that, let's say I'm sorry? Did I say to 0? I'm sorry, to infinity, yes. Okay, sorry. So yeah. So what will survive? And you can take all the terms that might lead to some such thing and keep track of them. and look at all the terms in which something has happened so that there's guaranteed to be, in the end, a negative power of capital N, or capital N minus little n, okay? And you can keep track of the stuff that will survive, and therefore you get an actual formula that may be useful. Now, this is, all right, this is what is called as opposed to the useless divergence formula. That's, I think, my invention. You have what Spiros calls the simple divergence formula. Now, so far, the simple divergence formula isn't even obviously coordinate invariant, because we did this non-coordinate invariant thing in order to get things started. Okay? But there is a cancellation. I wouldn't call it miraculous, but there is a cancellation. All the terms that are not obviously coordinate invariant cancel. That's presumably because this whole thing could have been done in a coordinate invariant way if we wanted to. I wouldn't call that miraculous, but there are then further cancellations. Large, as you go through this procedure, large collections of terms cancel completely for no reason that is at all clear. Okay, so there are multiple miraculous cancellations. Once you have observed the multiple miraculous cancellations, you get the superdivergence formula. So the superdivergence formula will say that if the integral of some I of g phi is equal to 0, okay, then I plus some exact divergences or some x divergences or something will equal 0 or will equal simpler or less important stuff. Now, all right, so therefore, all right, well, so before I say more about this formula itself, let me remind you, we had a lot of slides ago the useless divergence formula. Anything that integrates to 0 is the divergence of something, but that was useless by itself because the thing of which I was a divergence did not closely reflect the structure of I. And now what's going to happen in the superdivergence formula is that, well, let me describe it in one very simple case and you'll see. So, whoa. All right. So there's the superdivergence formula. What has just happened? Oh dear. All right. Can we get rid of that, and can we have some lights, and can we get rid of that? Because I see that my last few slides have somehow disappeared. That was clever of me. So this has to be lifted, and then let's have the lights on full. Thanks. All right. Okay, so let's suppose that our I of g phi contains a term like this. So remember, we're taking, let's put here, all right, well, let's do that. I guess there should be some fees also. Let's say that I contains a term like that. Now, notice that this, all right, now, when we take a trace, we have paired up the indices, right? And so this is not a complete description of what's going on. I have to tell you how to pair up the indices. But notice that one of the things I've done is to pair that guy up with that guy. And notice that this index appears in the same term as that index. I'm sorry. This contraction involves just one factor. There isn't, for example, the D maybe goes against that guy. That would be an external contraction. Okay? Let's suppose there is one and only one internal contraction like that in this term. What will the superdivergence formula give you? Well, this I plus a divergence of some other stuff is 0, or is made of simpler terms than, or less important terms than we started with, so that we're on our way to try to simplify the answer. And so what you do with this is the following. You take this guy out, and so now we have all right. So now, over there, all the indices have been paired up. Over here, all the indices except A have been paired up. This is a tensor of rank 1. We can take its exact divergence. Like that. Okay? This is the exact divergence of a tensor, and this guy with some sign, I think with a minus sign, appears in the superdivergence formula. Therefore, this guy is canceled by an exact divergence. And furthermore, an exact divergence of something that obviously very, very closely reflects the structure of the thing that we're canceling. That's the point. Now, I've described the superdivergence formula only partially and only in this very, very simple case. But this is the tool which one uses in a massive multiple induction. So the massive multiple induction is take your conformal integral invariant, look at all the contractions that appear in it, sort them according to some very complicated order relation so that one kind of contraction is declared to be more important or less important than another. Okay? So for example, contractions with more factors are less important. Yeah? Yes, Sergio?
So when you take that covariant quantity out,
yes.
it means you have other terms which would have
Oh, yes.
that they need. So why
Oh,
are
yes.
those terms better than the one?
Oh. All right. There is a 600-page answer to that question, okay? So I'm trying to describe let's see how to describe. All right. Of course, there are other terms, and so the claim is that there is some partial order on all possible contractions, which tells you which are more important than which others. And at each stage, you look at the most important terms and you do something to them. Now, what do you do to them? It depends. So, for example, for some kinds of terms which look, all right. For example, suppose you write the thing not in terms of curvatures, of ordinary curvatures, but in terms of vials and Weil-Scoutons. Okay? Now, suppose that there are no Weil-Scoutons, only vials, and suppose there are no internal contractions. What do you do with those terms? And the answer is there's something that involves the ambient metric. You can write down using the ambient metric something that is obviously conformally invariant that has those same terms. Okay? You then subtract it off, and what's left has only less important terms. And the induction continues. Okay? And that had nothing to do with the superdivergence formula. So there are various tricks. But at many, many, many stages, if the most important term is of a particular form, then you will use the superdivergence formula in order to know what to do. And what you do is you subtract off an exact divergence and what is left is somehow less important. Okay. In order to explain that more fully, I would have to explain the massive multiple induction. It already, I mean, you don't want to do it. Spiros and I have spent hours and hours going over the definition of the partial order, which is not simple. Okay. But that's the nature of the thing.
But is there a simple example where one can start with some simple formal expression and get through this step?
I think I should ask Spiros about that. I think the answer is yes. There are plenty of simple examples in which one can do these things in a simple way, and I think the way one discovers, I mean, part of what you do in discovering a 600-page proof is to work lots of examples. Yeah. So yes.
So for example, when the vial curvature vanishes, is there an easier way to see the structure?
Oh, so let's see.
Yeah.
Thank you. Why don't you? Okay.
So when
Why
the
don't you
vial
take it from
curvature is 0, the proof can be very much simplified.
You still go through the whole process of
You can have a much simpler process.
What about reach equals 0?
I don't know. I don't.
What does it mean?
Reach equals 0 is not conformally invariant. Reach is not conformally invariant.
Okay.
So I guess that it's
Okay. Sorry.
All right. So it seems to me that of this proof, I have succeeded in picking out the entertaining part. So I hope that you were entertained.